Anyway, let me get started then. So, it's a pleasure to welcome Andy Jackson to Stockholm and to our program. And he will give today's seminar about the beginnings of data simulation in geomagnetism. Andy is an authority in the field of geomagnetism. He has received his PhD in the University of Cambridge in the late 80s, and then has gone through a period of various postdocs, including places like Harvard and Oxford, and has then moved for a permanent position to Leeds, where he stayed for something like 11 years, and was then promoted to a full professor already in Leeds. But as some others that we know, including myself, that doesn't mean that you're going to stay there for the end of your life. And in fact, Andy took the consequences and realized it's a good idea to really move away from a place, even though you do have a permanent position. And so he moved to Switzerland to an even more attractive position. And so today he will tell us what data assimilation will bring towards geomagnetism in the future. Andy, please.
So, as they say, now for something completely different. So I will try to give you a feeling for the kinds of problems we're thinking about in geomagnetism. I realize most of you are in meteorology or oceanography, but I think you'll see the connection. So I've said the beginnings in my title, so because the first papers that discussed data assimilation in geomagnetism came out in 2007. So you will see that it's a relatively recent development in our field, despite the fact that you can all probably see that it makes a lot of sense. Maybe we're just very slow learners. So I'm going to talk to you today about the kind of data that we have available and that we can use. I'm going to choose to talk about an application of data assimilation that is not my own work. It was performed by a group in Grenoble and also Elizabeth Canet, who is in Zurich in my group. So this is basically the first application that I know of data assimilation. And then, well, I think that the longer-term secular variations represent an opportunity for us to use data assimilation. I would say that we are basically 25 years behind the rest of the world if the meteorologists are okay, but maybe we can catch up. So in many ways, that talking about the data means I'm talking about the past, the way we've assembled this data set. I talk about this exercise which represents the present, and I think that there are great opportunities in the future for using data assimilation for very long-term secular variations. So what do I mean by secular variation? Long-term variations are timescales beyond a few years, reaching out over decades to centuries and possibly to thousands of years. I mean, you probably know that the magnetic field exhibits very amazing range of timescales, including reversals every about a million years. We know the magnetic field has existed for 4 billion years, so there are plenty of timescales to play with, but I'm thinking more on the decade and century timescales. And the magnetic field is, of course, a vector quantity, and we can measure various aspects of it. Almost certainly the most common thing to measure is simply the declination here, the angle that a compass makes between true north and magnetic north. So that's been measured by mankind for at least 1,000 years, starting with the Chinese. And you'll see some examples of this kind of data. We can, of course, nowadays measure the full vector quantity in many ways, in the vector components or through the declination, the inclination, then the strength of the magnetic field. Okay, so here's an example of some data which does not project very well at all, does it? So this is the declination here measured in London over 400 years. And it just gives you an idea that the declination has changed in London from 10 degrees east through to 25 degrees west, and now it's heading back. So that's the kind of raw data that you have, and you'll see as you go back in time it becomes rather noisy, but nowadays we have observatories which can measure this change very accurately.
When was the meaning of the experiment?
Say again.
When was the experiment?
That is about 1840, but there's no real significance. If I showed you another place in the world would. Yeah.
Is this part of an oscillation, or you don't know?
Well, we don't have good enough data, but I would say that the Earth's magnetic field doesn't seem to be like the solar magnetic field. It's not a nice, regular, cyclical field. They're very different. This is much more stochastic. We have stochastic reversals. The interval between reversals can be very, very different. It's a very chaotic system, I would say, rather somewhat unlike the Sun. Now, if you were to take some of this good quality data from an observatory and look at the rate of change of the magnetic field. So now we've differentiated that signal. This is now the rate of change of the east component with respect to time. So it's measured in nanoteslas per year over the last 130 years or so. You see a much more complicated signal, of course, when you differentiate the signal. And if I can just, if we were to try and interpret this signal, so at the top of the core, okay, the field is originating in the liquid core of the Earth. If we were to write the equation governing the way that the magnetic field changes in time, we'd have an equation something like this: dB by dt is equal to minus v dot grad br minus br div horizontal divergence of v dot grad. The only reason I write that is to say that in a way, if you look at the rate of change of the magnetic field at the top of the core, dBr by dt, it's going to be proportional to the velocity at the top of the core. This thing is not going to change very much in time, whereas this possibly changes quite rapidly in time. And so I'm showing you this signal to show you that this is a bit like a proxy for fluid velocity. So that's what we're looking at, and it's basically proportional to v. So we actually think that the fluid velocity at the core surface is unsteady and is changing in time.
You're also assuming that the flow field is divergent.
Actually, I'm not, no. The flow is, yes, the flow, yes, sorry, div v is 0.
So the second part
incompressible.
It's 0.
It's incompressible. This is a horizontal divergence.
Okay.
So yeah, we believe that the fluid in the core is incompressible.
This is at the surface of the core. How does it relate with VR measure?
Okay, I'm getting a little ahead of myself, but it's much more complicated. You'll see there's a lot of messy things to deal with. I'll show you the data first. So I worked for about a decade with a historian, Art Jonkers, who helped to compile a data set that I'll give you an idea of what it looks like. Art also wrote a book about the historical aspects of navigation from lots of different countries, such as the Netherlands, the UK, France, basically the colonial navigation. So Art was a big collaborator on that. And we compiled data from people like this who this is someone taking a declination measurement on land. He's sighting the sun to find where true north is, and then his compass, of course, will tell him which way magnetic north is. So we put together this kind of data set for the 16th to the 19th centuries. We've recently trying to update that. There's about 250,000 data just about to be in that data set. Some inclinations, quite a lot of early data prior to 1700, and the intensity of the field could be measured since the middle of the 19th century. So it's actually only 150 years that we've been able to measure the full magnetic vector. So just to give you an idea of the kind of data that we have available, these are declinations then, the angle that the compass makes with true north. Through time, this is before 1590, rather sparse. The voyages like Vasco da Gama. And then as we go forward in time, of course, the distribution improves. Even in the even in the 17th century, you see that there are declinations measured over here in the Pacific Ocean. And as we go forward in time, of course, things get better and better. We don't just need declinations, we need inclinations, but you'll see that for the 18th century there are quite a nice distribution of inclinations, and of course that improves gradually through time. And then intensities these are actually only relative intensities prior to 1850, intensities in the 19th century. So you see that we've got a rather heterogeneous data set, just as many of you do. It's a tricky business to deal with, but nevertheless we have about 400 years of fairly good observations.
Question by Jenny?
Yeah.
Sorry, may I ask? Some years ago I was at a workshop in marine geology.
Yep.
And there was a researcher talking about how they could reconstruct how the magnetic pole changed in time using sediments and checking the direction of the...
That's right, yeah.
Could that be useful?
Yes, so I'll a couple of slides ahead I'll show you. But sediments, of course, you can go back hundreds of thousands of years, so it depends what you look at. We can see the last reversal in sediments, so that's a different type of measurement. It doesn't have the fidelity that we do, but it's certainly a possibility. Okay, that's the kind of distribution of data in time.
Sorry,
yep.
just for curiosity, this dip around 1800.
Oh, yeah.
Why is that?
You know, it's I don't know, and so we have not put together all of the data that I know exist. I mean, we've been selective. It's quite possible we could go and find some more data for this period. I don't actually know why. After this period, there was a big spurt in the exploration. For example, Ross went to the Antarctic here, and many countries were interested in exploring the oceans. So I don't actually know why this is like that. Maybe it was the Napoleonic Wars. I'm not sure.
So you have actually collected them all yourself somehow, not that you've taken them?
Yes, so they're all just being typed in from logbooks, basically.
Right.
It's interesting, there are exercises going on now on the internet where they're asking the public to help on this kind of thing. They put scanned images up, you can just register, you can try and type the scanned imaging. It's a very good idea. I don't know how successful it will be. Anyway, 15 years ago we did this ourselves, just sitting in the library with a laptop.
And is your record somehow now well known and available?
All of this data is publicly available.
And that's on the data site database in your...
Well, it's not actually sitting on a data site, but it's available if anybody wants it. I don't get very many requests, to be honest.
So you actually have to email you.
Yeah. This addresses your question, Jenny, because this is now for the last 10,000 years, and these are data that come from either sediments from various points around the world, or actual artifacts like fireplaces, pottery. When you fire pottery and let it cool, it can record the direction of the magnetic field. So this is a wholly different kind of type of data to the actual physical observations made by mankind. It's much more problematical. But anyway, we can go back to 10,000 years ago with a pretty good amount of data. So there are many different timescales of data available. So that just summarizes really the kind of data that's available. Now, so we're interested in the core of the Earth. The core, of course, contains liquid iron. It's gradually cooling. There is a convection taking place. The convection actually manages to create a self-exciting dynamo. So the convection creates electric currents. The electric currents create magnetic field. And we believe that that's gone on for 4 billion years. Of course, we make our measurements not at the core, but we make measurements here at the Earth's surface. And there are contaminating effects. For example, the crust and the lithosphere generate magnetic fields. The space environment generates magnetic fields. So these are sources of noise, as far as we're concerned. We really want the field from the core. But the signal-to-noise ratio is pretty high. It's about, let's see, 40,000 divided by 200. It's about a factor of 2,000. 200 is the signal to noise. So it's pretty good. So the first thing we need to do is to relate our measurements to the core, to the field here at the boundary between the core and the mantle. So to do so, we assume that the mantle is an insulator, which is a pretty good approximation. The mantle is largely made from silicate materials. Its conductivity is about 10 to the 5 times smaller than the conductivity of the core. So the first thing to do is to take our data and look at what the magnetic field looks like at the top of the core. And I'll just give you a feeling for how these two things differ. So what I've plotted here is the radial magnetic field measured at this is at the Earth's surface. So this tells you the number of magnetic field lines per square meter which are entering the Earth here. They're exiting the Earth here. And what we're going to do is we're going to map this field through the mantle onto the core surface. And I've used the same color scale so that you have a feeling for how the amplitude changes, because of course as you go closer to the core, the amplitude gets higher. So I'm keeping the same color scale. All we can see here at the moment is the dipole, the nature of the field. But as we go through the mantle into the core surface, the field gets stronger and stronger and more localized into little spots. And you'll see that it's localized, for example, here at these high latitudes. And then also there's a few spots here which sit over Africa.
Is it exactly vary like 1 over r square, or is it more complicated than that?
So the dipole goes as 1 over r cubed, and then the multipoles go even stronger. So we're restoring those multipoles as we look in the mantle. So what we've done so far is to seek a very smooth representation of the data, which is which represents the field at the core surface. So this has nothing to do with data assimilation yet. This is pure, simple modeling, shall we say. We look for a time-varying magnetic field which is a function of both space and time, and which agrees with the data set of observations that I've shown you. And we put together this model for the last 400 years called GUFM1, and you can see here are these strong patches of field. This is at the core surface now. You'll also see that there are these features which gradually drift west in time. So, for example, this feature starts out right here in the Indian Ocean, and although it grows and well, sometimes almost disappears, you can see that it gradually moves across Africa over the 400 years.
Sorry, I'm a little behind here. How is this determined? Is it through that equation that you were in?
So that is determined by simply. So here's the core. Here are the data, and I assume that there are no electric currents in either in the atmosphere or in the mantle. So the curl of the magnetic field is 0 both here and here. And I simply want to reconstruct, this is what we're looking at now, is the radial component of the magnetic field here on the surface of the core. So I just have a simple inverse problem where I want to reconstruct BR as a function of theta, phi, and t on that surface, given all that sporadic data all over the Earth's surface. So it's, and we have to apply some smoothing. You could say it's a very ad hoc smoothing, but we just look for a smoothly evolving picture in time.
How many data points do you use from the surface on one given time?
So over 400 years, there are in excess of, I think, 350,000 data.
Right. But you at one given, do you assume them to be at the same time, the data, now when you reconstruct this, or do you actually...
We take anything we can get. We assume they are all independent. Yeah, we have a time-dependent model, and we just take all the data and we assume they're all independent measurements of
But then some data assimilation technique would be the most appropriate.
Yeah, it's clear that that's for the future, I think, but it's clear that if you could have a dynamical model for what's going on here, and you've got your data, it's very clear that that's a very good way to go. And that's what various people are gearing up to do, but it's still early days. So, in a way, this now represents our raw signal here at the surface of the core. I want to show you something that has been done with data assimilation. So, in fact, your comment was absolutely right. The challenge is, let's move beyond the mapping approach to something that takes into account the dynamics, and let's see if we can infer something about the properties of the interior of the core. Because we know from numerical simulations that the magnetic field in the interior of the core is a lot different. This is a famous so-called spaghetti diagram. The field in the core is a lot different because of the dynamics that's going on from the field which lives outside. These would be the measurements we take, but then as soon as the field line goes into the core, it's wrapped up by the fluid motion. And there are two types of magnetic field which are in the core of the Earth. We would call them colloidal and toroidal fields. I mean, there's an obvious. You do this in meteorology and oceanography. You represent an incompressible fluid. There's a colloidal and toroidal expansion, probably.
That's what we do is actually along the surface of the Earth actually represents field which can be both have a non-zero divergence and not the zero vorticity, of course. Yeah. But only we do that actually only in 2 dimensions at the surface of the Earth. So slightly lower. Yeah. It's actually the same thing.
Okay. Similar. Yeah. This is the 3-dimensional.
But we don't feel the expression toroidal and toroidal.
So these colloidal fields are the ones which manage to escape from the core of the Earth. There are toroidal fields which are wrapped up inside the Earth, which we actually can't sense. But these would be important for the dynamics. So one challenge is can we find out anything about the toroidal field in the Earth's core? There are reasons for thinking that this might be quite a bit stronger than the colloidal field that we measure. So here are the first order questions. What's the strength of the magnetic field in the interior? What's its division into toroidal and colloidal components? How are fluid motions organised? Now, I want to, so this is now not my work. I just thought I would choose this and show you what people have managed to achieve so far. And this is a paper which I was telling Olivier came out just last year in 2010. It is I think the most important result and essentially the first application of data assimilation techniques to the Earth's core. And I call it seismology geodesy of the core, and I hope you will see why. Let's first of all just look at the physics of the way the magnetic field evolves. So I already used this equation in a way on the blackboard. We have the rate of change of the magnetic field. This is everywhere in the core. Is given by two contributions. The first contribution is comes from advection. So U here is the fluid velocity acting on an existing magnetic field, and this creates change in the magnetic field through motional induction. It moves magnetic field lines around and generates currents. And then the second part is diffusion. So this is because the core is a finite conductor. Okay, it has a finite resistivity. We think that the resistivity is similar to the resistivity of iron at the Earth's surface. So the first thing we can do is we can look at the relative contributions of these two terms. So there are timescales associated with these two terms. This term here, del squared B, has this thing eta. Let's see, eta is 1 over mu naught sigma. Mu naught is the permeability of free space, and sigma is the electrical conductivity. So we think we know what eta is for the core, and we can work out a timescale for the diffusion in the core. It's basically the same timescale as you would have for heat diffusion, L squared over eta, which would be about 30,000 years. Whereas if you take a fluid velocity which comes from an estimate, for example, you remember that patch which I showed you moving across Africa, that gives you an idea of what the fluid velocity might be in the core. It turns out it's about 20 kilometers per year. So if you take the timescale for advection, it's something like 60 years. So 60 years so this is the core. 60 years for a fluid parcel to go from, for example, the bottom to the top of the core. So 100 years as the overturning time for the core. Now, you'll already notice that this is much shorter than this. So if we're going to work on the timescale of a few decades, you can see that there's going to be hardly any diffusion taking place in the core, and most of what we see is going to be due to advection through a fluid flow. So the first thing that we do is to we might say that we take the core to be an ideal fluid. In other words, we take its electrical conductivity, so this sigma, we take its conductivity as infinite. We think it's a superconductor. That means that there's no diffusion taking place, and we just don't worry about that term. So that's the first approximation that we make, and it's quite accurate on the timescale of decades, we think. Now, I'm not sure if I want to show this, but I think everyone in the audience knows about rotating fluids, don't they? you're all meteorologists and oceanographers, you know.
Beautiful movie though.
You want to see a movie? Okay, it's just a 2-minute movie, rotating. Sorry, this is a dish full of 10 centimeters of fluid. This is rotating at 10 revolutions per minute. That one is not rotating. This is a mirror at 45 degrees that allows you to look into the side of the fluid. And as I'm sure you all know, there's going to be a great difference between the non-rotating and rotating cases. This one has got a camera in the rotating frame, and you put a bit of dye into it, and of course in the non-rotating case, that dye just diffuses very isotropically. The dynamics of a rotating fluid is completely different, as you can see. As you see, looking down, looking from the side of the fluid, well, anyway, you can see that basically the fluid has a rigidity along the rotation axis, so that the same velocity takes place here as here. I'm sure you're all aware of this, but this is the Proudman-Taylor theorem, which says that the fluid moves as if a column were rigid about the rotation axis. Okay? So that was just to remind us how rotating fluids are much different from non-rotating fluids. And that's important when we think about how to set up the dynamics of the Earth's core. So what is very popular as a way of representing short timescale dynamics is, again, I heard this morning, you know all about this, the quasi-geostrophic approximation. Now, the QG approximation is been very successful for the atmosphere, shall we say, but there are a lot of simplifications that go into it, and it's not obvious that you can apply it to a thick body like the core. For example, it's correct when the boundary of the fluid is either flat or very slightly sloping. But there are regions in the core where the boundary, at the equator, for example, the boundary becomes vertical, as in the atmosphere. There is also the fact that we have a magnetic field in the core. All these things can break quasi-geostrophy. A magnetic field could, in principle, break quasi-geostrophy. So the Grenoble group, nevertheless, have done a lot of both physical experiments and also some numerical experiments which make them believe that the QG approximation is a good one for the core, especially for short-term dynamics. So this QG approximation says that everything is rigid, basically, in the core, and that whatever is happening up here is happening down here. You also have a small, the problem is you also have to agree with the boundary conditions, which means that there is a small vertical flow induced. Anyway, this is the basic idea for the short-term dynamics of the core. I think we can certainly argue whether it's correct or not. Seems to be a good approximation. Right. Now, I just want to tell you about one other thing before I show you what they've done with data assimilation, and that is concerning the length of the day on Earth. So the Earth is spinning with a period of 24 hours, but it undergoes small fluctuations of about 1 part in 10 to the 8. Here's the basic data. This is over 150 years. All of the atmospheric physicists in the room know that if I look on short time scales, I have a very strong signal associated with that angular momentum change between the atmosphere and the solid Earth. And there's probably a small oceanic component as well. So we've been able to measure the rotation rate of the Earth with precision for precision, I suppose, for the last 50 years since the introduction atomic clocks. If I take the Fourier transform, if I look at the spectrum of this signal, this is the kind of spectrum that you see in there. Obviously, as you go to longer periods, there are long period signals, but there is this strange bump here in the length of day, with a period of about well, between 6 and 8 years, which no one can explain. And if you look in the atmospheric angular momentum, for example, the atmospheric angular momentum is this line here, and the atmospheric angular momentum certainly does not contain a signal in that period.
What is the dash curve?
So the dash curve is I believe what happens when you subtract the atmospheric angular momentum from the length of day to see what's left, and so that would be what is left. So it's been a question where this bump in the length of day spectrum comes from. And of course, when you run out of candidates, everybody always tends to turn to the core of the Earth and say, okay, it must come from the core. So this is what motivated the Grenoble group. In the core, we know that there are some normal modes which can consist of so-called torsion oscillations. They are cylinders of fluid which are able to oscillate back and forth with a differential rotation. It's a normal mode of the Earth, and you might wonder where the restoring force comes from. I say they're governed by a wave equation. The restoring force, so if we're now looking down one of those cylinders, the restoring force is from magnetic tension. So if you have a magnetic field threading through between two cylinders, magnetic fields are like elastic strings. They don't like to be stretched. If you stretch them, they'd like to go back. So if I have this magnetic field here threading through two of these cylinders, and I rotate the cylinders differentially with respect to one another, I will distort that magnetic field, but the tension wants to bring the cylinders back to their original. So you can actually have these kind of oscillatory motions in the core. It is a normal mode of the core where the magnetic field plays the role of the restoring force. And you can also imagine that the period, the fundamental period of this oscillation will depend strongly on the strength of this magnetic field. In fact, it's proportional. Let's see, the frequency is proportional to the field. The stronger the field, the faster the oscillations. So if you could see these oscillations, you'd have a very good way of measuring the magnetic field strength. So, let me now tell you what the Grenoble group have done. It's a little bit of a long story, but they take the field model, which we've looked at already. The field model is a function of theta, phi, and t. They then they use the induction equation. And they use this quasi-geostrophic approximation for the flow velocity. They use both of those assumptions. They also use this assumption that the conductivity is infinite. And all of those go into the production then of a flow model. This is V, a flow model at the top of the core. So this might be an idea of the kind of flow that they think is taking place at the top of the core. Again, we're still working at the top of the core. We have not managed to go inside the core yet. And then what they do is they extract only the zonal component of that flow, because they're interested in looking for these torsional oscillations. And when they just look at the zonal component, this is now a plot showing the as a function of cylindrical radius. So this is now the axis of the Earth. This is now the equator. These are the zonal flows, and what they see is that the zonal flows alternate and apparently propagate from this point here towards the equator. Now, actually, this point here is the inner core boundary. I haven't told you this yet, but this is the core of the Earth, and the core of the Earth has a small inner core. So what we're looking at here is a plot showing the propagation of zonal flows, and this point here. Sorry, I'm keeping you busy. This point here is the inner core boundary. So we're seeing these flows propagate out from here to the.
But again, what is the quantity that is shown?
So that quantity is V phi, the phi component of the flow, and it's axisymmetric.
So the cylindrical radius is projected on top of this surface. Is that what it is?
Yeah, we're looking down. Yeah, exactly. So actually, what we're everything is in the equatorial plane, and then we measure everything in the equatorial plane. This would be the coordinate S. S is 1 here. S is point 3. I'm not quite sure. 0.35 or something. This point here.
So that's at 0.35.
Yeah.
Right.
Let's see it.
These are fluctuations in these velocities, right? It's not the velocity, but the fluctuations.
This is the full velocity.
I mean, minus the average velocity. Because it's rotating. The day.
We're in the rotating frame. Yeah, we're in the rotating frame. I actually don't know if there is a mean or not, which is being subtracted, but I suspect not. So what you're seeing is that you have these propagating waves propagating from the inner core out to the equator, and they are going in one direction, then they're going in the other direction. Now, you can...
How about north-south asymmetry?
The QG approximation has made everything equatorially symmetric. It's a strong initial assumption.
How was the initial condition? How did they define it? Initially?
There's no... this is all kinematic. This is all observations so far. In a couple of slides we're going to need that kind of thing. So far it's observational. So the first thing to notice is if you're basically imaging these kinds of oscillations, and if you know what the flow is everywhere, you can work out what the angular momentum is in the core, and you can therefore predict what the angular momentum of the mantle would be, so you can predict how the rotation rate of the Earth will change. So this is all, again, a purely observational procedure. And this is, in green, we have the length of day in milliseconds as observed astronomically. In black, in black we have the angular momentum predicted by these observations. And there's one called a simulation in red. We'll get to that in a moment. But for the moment, green is the observed astronomical data, and black is the predicted length of day from this calculation that involves geomagnetism. So this is quite, for me, this is quite spectacular. Okay, there's two clear things. They get the correct amplitude and they get the correct phase in this band. I think they've filtered between maybe 5 and 8 years.
Is correct amplitude in which sense?
In the sense that this prediction, this black prediction, has basically got the right amplitude to explain the missing signal, the signal that we don't understand.
In the spectrum, in the earlier spectrum that
in the earlier spectrum, yeah.
Ah.
Yeah. So, okay, that's quite.
There's no drift. I mean, no trend even. It's extremely stable.
Well, I don't know about the details. Axel, this is not my work, but you know, there's a small. Obviously, this doesn't fit as well over here as it does in the middle, but certainly the phase is right. I mean. Now, here's where the data assimilation comes in. So we have this signal now we'd like to understand, and we have an understanding of the physics of what governs this propagation. It's those magnetic field lines providing tension. So the equation that they need to solve, omega g is the angular velocity as a function of cylindrical radius. So this would be the thing that they observe. They have the 2 omega g by dt squared. It's a wave equation, and they have omega g here. It's basically d by ds of omega g. It's a wave equation with a little bit of damping. And the key thing that they want to get at, everything here is known apart from b squared, which is the strength of the magnetic field lines threading through the cylinders, which provides the tension. So this is what they'd like to solve, and they use data assimilation to do that. Let's see. And as I understand it, this is not my work, but they because of the oscillatory nature of this signal, they actually take a driving here at the inner core boundary. So they take a driving. They're going to find the strength of the driving here, and then they just let these waves propagate out through the core. And what they're able to do.
So that's an inhomogeneous thermal equation or initial condition?
It's a boundary condition.
Yes.
It's a constantly oscillating boundary condition, and then everything just floods out from there. So it seems to me that's an assumption. They're assuming there's some kind of fluctuating boundary condition, and then the waves just fly out from the inner core. So these are the observations that you've seen before. They actually choose just this little box here to assimilate. So those are the observations, and then this is their assimilated solution. It has this. I think it's a purely sinusoidal boundary condition down here. They have to tune the strength of the driving. They have to tune the amount of damping that they have in the wave equation, and then they try to discover the magnetic field strength. The magnetic field strength governs how quickly the waves propagate. So you see, for example, in both the observations and also in the assimilated solution, the waves are propagating more quickly here than in the interior. Yeah, I think it's the opposite.
What you call observation is actually also based on a model. I mean, it's not really observation.
It's based on a lot of processing steps, but it's some kind of theoretical smooth version of observations. mean, we've gone from data, we created a magnetic field model, we made a lot of assumptions, we found a flow model,
Yeah.
but ultimately it's data. There's been no dynamics has entered yet.
But it's still based on a model. You don't really integrate it forward. It's more static model.
It's a model in the sense, I mean, I would agree with you, there are some assumptions gone in here. QG representation of V is a model, but it's purely kinematic. There's no, at every instance
Yes,
of
but I
time.
think there's also some kind of assimilated solution, not really observations.
I think it's definitely not assimilated because there's been no dynamics has entered anywhere here.
It's something like what we call an objective analysis, I think, that sort of combines data with some theoretical assumption of the state.
Also, the
V
universe,
is
I mean, the universe of this would be observation operated. So it's a kind of observation operator. So instead of mapping model space to the observation space, then you can map the other way around and then provide that.
V is given for the start and not modified in the process. Velocity V.
B at any one point in time is determined from observation.
Okay.
And I realise there's a language problem, I knew there would be, but there's been no dynamics has entered at this point. These are just somehow some kind of snap estimates of what the flow would be. It's like making a wind speed measurement. I make a wind speed measurement now, and then I go out another hour later and I make another one.
Okay.
Is it okay? And that it's only, I believe, it's only at this point. Here's where they use a simulation. This is a prognostic equation that they're going to try to make sure that those velocities agree with. Okay. This omega g is basically equivalent to my velocity v. So that's the prognostic equation we tried to use to do simulation. So I agree with you. These don't look like observations, but there's nothing else in there apart from observation, and a lot of kind of strong. What was the word you used anyway? Modeling.
Objective analysis.
Yeah. So I'm nearly finished. What they get out is an estimate of the root mean square magnetic field strength in the core. That's the thing which governs the speed at which these waves propagate. So for me this is a very big deal because we've never had such an estimate before. I mean, in many ways I think we probably know more about the interior of the Sun, especially from helioseismology, than we do about the interior of the Earth. We knew this value here, right at this is now cylindrical radius, so this is the boundary, this is the equator. We knew that value. It's about 0.3 milliteslas, that's okay. What we didn't know, and you'll see that there's a huge spread, basically that you can only put a lower bound on the value of the magnetic field. And the reason is, see if I can get this right, in this region here, the waves are travelling very fast. You see, it doesn't take very much time to go from here to here, and so it's very hard to know whether well, basically the tilt of that is very small. If it were vertical, the waves would be travelling infinitely fast, which means the field strength is infinitely strong. So the fact that that's only a very slight tilt means it's very difficult to get the actual field strength. So you can put a lower bound on the field strength, but it could be higher. Now this is already a very interesting number.
Sorry. B, what is the...
It's the S component of B. It's the component of B perpendicular to the rotation axis.
And the various scales correspond to various spaces?
Correspond to various different inversions, but I don't really know.
In the same data but different.
Same data but different. Not quite sure. Oh, you know what? It's with different regularization parameters. Of course, you have to do some smoothing. So, yeah. I think the key thing is that you can't go lower than this value, otherwise the waves would travel too slowly. And you can see they're traveling pretty fast.
The field was actually, the BS was time independent, right?
Yeah, they assume BS is time independent because you're just, it's like, this is like seismology of the Earth. These are just oscillations on a background state.
How come there's no phase mixing in the radio? Well, it is probably. I don't know. No, maybe we can't talk about it. I don't know.
So I can virtually finish here. The key thing is that this is an interesting number for a geomagnetist. This is now 10 times stronger in the interior than this value here. And we have a lot of numerical simulations of magnetic field generation in the core. And a lot of those simulations tend to show that you have about a factor of 10 increase in the field strength as you go inside the core. So this makes an awful lot of sense geophysically. It is, I believe, one of the first real measures of the field strength inside the core. If it's correct. I mean, I'm showing you what they've done. I think it's all very impressive. There are lots of reasons why it might be wrong, but if it's correct, then this makes a lot of geophysical sense.
And that field is essentially toroidal?
Beg your pardon?
Is that field component essentially toroidal then?
It's a mixture actually, because it is the S component of, so it's this component in this direction, the S, and it actually has a mixture of both colloidal and toroidal components, but it's certainly going to have some toroidal field in there.
So when you say one, there is the outer radius, right? Not the surface of the Earth.
One here is the equator. So again, we're just, this is the coordinate S. This is S equals 1, and this is S equals 0. And everything here is has been averaged in Z. Sorry, this would be Z. So what we've got here is it says an RMS BS. It's an integral of where this is, so it's an average over Z, and this is a plus H, this is minus H. It's all appealing to this quasi-geostrophic assumption that everything is doing the same thing in Z. So you integrate over an entire column, and you integrate in phi to get this kind of average. And this is the root mean squared, so this is now in milliteslers. Okay, the IGRF, so I'll just move on to the last two slides. The IGRF is a standard description of the field. It's built into most mobile phones, for example. This is the iPhone. And it has a predicted element, and this is just to let you know that for the first time a data simulation solution was used in this predictive element for 2010 to 2015. This is the work of the group in the US at NASA Goddard. So we're on the cusp of starting to use these kinds of techniques. So that's my summary. There's lots of observations. Only 3 or 4 years ago, the first papers on data assimilation. I've given you this example. I think that's a major impact. We've never had this constraint on the magnetic field. strength in the interior. You know, I encourage you. The field is largely wide open. You're far more expert than most people who work in this field. I think there's a chance for contributions from anyone who wants to get involved. So, thank you.
Thank you. Questions, please. So it's quite a dramatic, of course, to have such a 6-year oscillation in the Earth core rotation rate. It's quite surprising. I mean, did anybody actually expect anything like this? Ever?
Again, so I don't really know. I mean, I think it's been well known for a number of years that that signal. I mean, we looked at it in the spectrum here. That bump has been around and has been unexplained. I think the key thing is
since 2000, yeah.
Well,
before that, even.
But I think even before
Even
that.
before that, right.
No one has really looked. And okay, I tried to give you a very kind of enthusiastic view on this work. I think it's fabulous, and yet there are some little worries because if you go back to the original data, I showed you some observatory data. We have these are, so for example, these are monthly means. You will struggle to see any 6-year signal in this raw data. So what is going on? There's some kind of big stacking exercise, I think, that has gone on to be able to pull this signal out. These are the things that worry me when there's nothing you can see in the raw data. You have to go through some elaborate processing techniques and it's going to be very difficult to work out where there's a weak point in. I mean, there are many things that are open. Whether the QG approximation is a good one for the core, I think is wide open. Anyway, I think it's an interesting area of work.
Yes, okay, please.
I know very little about this, but I could imagine that the regularization you made in combination with the biases in the data might create interesting effects.
These are the kinds of things I worry about. There's been some ad hoc smoothing gone on to create this model. There was some smoothing that went on to create this model of V. Then there was some bandpass filtering, and yet, you know, you do have this, at least this independent verification. They do get the amplitude and phase correct. Could it happen by accident? I don't know. I mean, maybe it could. I don't know. So it's not clear what status this has. I mean, I think it's a very exciting effort. Whether it's right, I don't know.
But I guess, I mean, having the data accessible for everybody, I guess there might be people who could sit with that particular problem and really explore it systematically, how biasing and how the model and regularization, how they could interact, or interaction could be avoided.
I mean, I think we come back to your question early on, which is that it would be much better to do away with all of these ad hoc intermediate steps, right? I mean, now we've got an idea of something we'd like to test. We should be able to go from that model via data assimilation using the original observations without all of these intermediate steps, right? Then you would feel happier because you would understand what's going on. You've got some kind of dynamical model and you've got some observations. And, I think that's obviously for the future.
Is there a possibility of expecting such things for other planets, or do they have to have a?
Well,
I mean, like giant planets, they have so many years, but
sure, why not, Axel? I mean, you know, if all of these planets will have that. The torsion oscillations are a normal mode that everyone expects, right? Maybe if we go to Jupiter with Juno, But you know, the time period we're going to observe Jupiter for is rather small. Okay, we're at Mercury now.
Yeah, but the period may be much shorter than 6 years.
The periods we wouldn't know until we. It depends on the field strengths.
Yeah, that is very strong.
So for Mercury is very weak.
So yeah, but for Jupiter, which is only gas strength.
Jupiter is probably very strong, so that would have a fast oscillation period.
Yes.
Yeah. Mercury is probably too slow.
Yes? Any other questions? Why does one actually call it declination? I was wondering, I mean, the magnetic field, we're all used to this from school, of course, but I was curious because in astrophysics, declination is this angle, and azimuth is this angle. So why does one choose this? Do you know? Talk about magnetism, geomagnetism, about declination instead of something else.
Well, it's had many, in the English language, it's had many terms. Going back hundreds of years, it was called the variation.
Yes.
The magnetic variation. Right? At some point, declination became more common.
Well, in the astronomy, I mean, it's the way the star declines from the direction towards the pole. And this is a similar thing. I mean, the way the needle declines deviates from the direction towards the pole.
Yeah, I see. Yeah, that really is. Okay. That's fine. Good. Yeah, thanks for the illumination. Any other jokes? No? All right. If that's not the case, then let's thank Andy again. Okay. So that's really as far as data assimilation today is concerned, but there is. For those enthusiasts, the possibility to listen to a turbulence seminar that Yukio Kaneda will give here in this room at 3:30. So that's about the three nons of turbulence: non-equilibrium, non-stationary, and non-linear. And maybe some other nonsense he says. Did you say that? It wasn't the title, right? Nonsense, yes. So,